Hello everyone. In this lecture, we will learn about graph traversals and their implementation using practical examples. As an overview of this lecture, we will have a look at definition of graph traversal, explanation of known algorithms in graph traversals such as depth-first traversal, also known as depth-first search, breadth-first traversal, also known as breadth-first search algorithm. We will also implement those algorithms using practical examples on Java for depth-first search and breadth-first search. Many graph applications need to visit the vertices of a graph in some specific order based on the graph's topology. The goal of a graph traversal generally to find the edges to be used in the search process without creating loops. This means that with graph traversal, we can visit all the vertices of the graph without getting into a looping path. In an undirected graph, we follow all edges. In a directed graph, we follow only out edges. There are two commonly known graph traversal algorithms for unweighted graphs. One is depth-first search algorithm and breadth-first search algorithm. In depth-first search algorithm, a starting node is selected and explored as far as possible along each branch before backtracking. Backtrack is an occurrence when the visited node no more has an adjacency node that are not visited. In this case, we keep popping the top vertex from stack until we reach to the node that is unvisited or has unvisited adjacent node to it. From the example below, let's take vertex or node 1 as our starting node, which we defined as our root node at the visualization below. But before, I also want to inform you that the animation below will not be the exact behavior of how depth-first search algorithm would behave when we would need to implement it on Java. This representation is only for familiarizing with the behavior of depth-first search algorithm rather than accepting it as core depth-first search implementation logic. So this said, let's look at the behavior of the depth-first search algorithm given at the example below. The starting node is marked as visited and pushed onto stack. Next, we select next adjacent node to visit. At this point, vertex 1 has two adjacent nodes or vertices as vertex 4 and vertex 0. Selecting one of the adjacent node depends on how the graph is structured and also how the algorithm is implemented. So in our case, let's take vertex 4 as the next node to visit. We push it onto stack and output it. Vertex 4 has three adjacent nodes or vertices that we can visit. So we select vertex 2, again we mark vertex 2 as visited and push it onto stack. At this point, vertex 2 has two adjacent nodes such as vertex 4 and vertex 0. We have visited vertex 4, so we skip it and push vertex 0 onto stack. Mark it as visited and look for the next node to visit. Vertex 0 has two adjacent nodes, but they both are visited. So in this case, the algorithm does backtracking. Backtracking happens when an adjacent nodes of a current node have visited state. In this case, we start popping from the stack and check the next vertex in the stack until we find a vertex that has unvisited adjacent node. So we pop the top vertex and next vertex is vertex 2. Vertex 2 also has two visited adjacent nodes, so we pop again. The next vertex is vertex 4. Vertex 4 has one unvisited adjacent node, which is vertex 3. So we visit vertex 3, push it onto stack, and output it. As we now have visited all the vertices in our graph, the logical behavior of depth-first search algorithm will be keep checking adjacent nodes and pop from the stack until it finds an unvisited adjacent vertex. Graph has no more unvisited adjacent node, so we have the output when the stack is empty. Breadth-first search is another algorithm for traversing through our graph. It uses queue data structure to track which node to visit next. Same as in depth-first search algorithm, we can choose any node as starting node in our graph and traverse through the graph by visiting neighbor nodes first before moving to the next level neighbors. This statement will make more sense as we go through the animation below. So, as you remember, depth-first search algorithm explores the graph as far as possible along each branch. In breadth-first search, however, connected nodes are leveled depending on the starting node and the nodes in the same level are visited first before jumping to the next level. So to understand this definition better, I will split the graph into levels considering the starting vertex. If we level our given graph, it will look like this. We have vertex 1 at level 0, vertex 0 and vertex 4 at level 1, and vertex 2 and vertex 3 at level 2. Let's put the graph left and see how queue data structure is involved in the process of traversing through the graph. So we have starting node vertex 1, we assign it as visited, add it to the queue, and output. Vertex 1 gets dequeued and we visit next level neighbor vertex 0 and add it to the queue. Vertex 0 has a neighbor at level 1, so next we visit vertex 4 and add it into the queue. There are no more neighbors at that level, so we dequeue the vertex 0 and output it. Next level neighbor is vertex 2, we visit it and add it into the queue. At level 2, vertex 4 has another neighbor, which is vertex 3, so we visit it and also add it into the queue. No more neighbors left at level 2, so we start dequeuing vertex 4 and output it. Vertex 2 has no next level neighbors, we dequeue it too and output it. Same for vertex 3, basically no more vertices to visit, we will dequeue it and will no longer have nodes in our queue. As our queue is empty, the algorithm finishes and we have the output. In this practical example, we will look at how depth-first search algorithm is implemented. For convenience, I'm not changing the structure of our graph list and conducting our practical work on the same graph structure we had in the previous slide. The graph structure we have here is created using adjacency list, and this list is represented as graph list variable in the code example. So for convenience, we also can visualize how our adjacency list will look like. So this is the adjacency list representation of the created graph you see at the very left of the screen. We can start from vertex 1, just like in the previous slide. In line number 2, we are just showing on command line for depth-first search traversal result. At line number 4, we need to keep track of visited vertices, so we need to declare a Boolean type array that takes the same size as the number of vertices in our graph. In default, all indices of the created Boolean array are set as false. At the next line, we also declare stack data structure to maintain 3 important aspects of depth-first search algorithm. 1. To avoid looping, 2. For backtracking, and 3. To know when our algorithm is finished. At line number 7, we basically push our starting vertex into the stack as initializer of our while loop for the algorithm. At line number 9, we are basically executing our algorithm until our stack is empty using while loop. At the next line, we are popping our starting vertex from stack and keeping the value at the start variable. Check if the visited Boolean array's start index is false, because if it is false, we need to set it as visited by changing the state to true. As you can see here, it is false, so this if condition will be executed. At the next line, we change state to true and print our first vertex in our graph. Next, we are declaring a linked list of adjacent nodes where it is equal to index of the graph list we have. As we are taking index start from our graph list as new adjacent node linked list, new adjacent node linked list will be storing vertex 0 pointed to vertex 4. And if you pay attention, you will see that they are the actual adjacency nodes for vertex 1 in our graph. Next, we are basically creating a for loop which will iterate through the connected nodes of vertex 1. At the next line, we are declaring a local variable of dest, stands for destination, and making it equal to the I index of our created adjacent node linked list. This way, we will be able to reach adjacent nodes of vertex 1. At the next line, we check if dest index in the visited Boolean array is visited. If it is not, then we push that vertex into the stack. Vertex 0 is not visited, and it is equal to false in visited Boolean array, so we push it into the stack. At the next iteration, we are at vertex 4. It is also not visited as its state is false in visited Boolean array. So we push it to the stack as well. At the next iteration, I is no longer smaller than adjacent node size, so we finish the execution of our for loop. Back to line number 9, our stack is not empty, so we proceed again through the while loop. At the next line, start variable will now be equal to vertex 4 and vertex 4 will be popped from our stack. Next, we check if vertex 4 is visited. As you can see, it is not visited yet, so we execute the if condition and change its state to true and output it. Next, in line number 15, we need to get the adjacent nodes of vertex 4, so we override 4th index of our graph list on our adjacent node linked list variable. Adjacent node linked list variable will now have 4 variables in it starting from the beginning as vertex 0, vertex 1, vertex 2 and vertex 3. At the next line in line number 16, we now aim to visit one by one all adjacent nodes of vertex 4 using for loop. At the first iteration, dest variable will be equal to vertex 0. In line number 18, we check its state in visit boolean array if it is false. State of vertex 0 in visit boolean array is false, so we push vertex 0 again into the stack. In the next iteration, dest variable now will be equal to vertex 1. We do the same thing again. We check if it has unvisited state. And no, actually it has visited state in our visited boolean array. So we skip the if statement and get to the next iteration. At the next iteration, dest variable now will be equal to vertex 2. We check the state of vertex 2 in visited boolean array. It is false, so we push it onto the stack. Next iteration and the last iteration is vertex 3. It has false state in the boolean array, so we push it onto the stack. We finish the for loop and get back the while loop again. Stack is not empty, so we still need to iterate through our while loop. This time start will be equal to vertex 3 as it is the top node in our stack. And we pop it from our stack. We check if it has visited state true. It doesn't. So we change its state as visited, which means true. After changing the state, we output it 2 and again override on our adjacent node linked list, this time by taking the 3rd index from our graph list. 3rd index in our graph list has only one node connected from head node, so we basically go once through the for loop. In the for loop, we get to the 1st index of adjacent node linked list. It is vertex 4. We check if it has visited state as false. No, it doesn't, so we basically finish with the for loop and get back to the while loop again in line number 9. Next start vertex will be the top vertex in our stack. It is vertex 2. So we assign start vertex 2 and pop vertex 2 from our stack. At the next line, we check its state in visit boolean array. It's not visited, so we change its state as visited and output it. So from now on, we basically repeat the same thing. So I'll just go through the for loop and we continue in slow pace at the next while loop. At this point, you should notice that the only vertex we have in our stack is vertex 0. So this means we will backtrack now until we get to the point where there are unvisited adjacent nodes or until the stack is empty. Backtracking would have true meaning, however, here, if we had an unvisited node somewhere in the graph, but it's not a problem because the ID is still there. So you know that from this point on, we would basically pop until we see that there are unvisited vertex in our stack. So now we will do last pop and visiting for vertex 0 and basically iterate through the loop until we have an empty stack. So again, I will be executing code in slow pace and you will notice that we will have couple of iterations just for the sake of algorithm and finish our depth first search implementation. At last 3 iterations, I didn't indicate adjacent node linked list below, because it is same linked list iterating through the first index of graph list. So we basically iterated through the vertex 0 as many as we had in the stack and finished the algorithm when the stack was empty. At the next slide, we will see how breadth first search algorithm is implemented using practical example. For the implementation of breadth first search algorithm, we will use same graph structure as we did in the previous slides. This said, let's look at how breadth first search algorithm is implemented. At first, we input the starting vertex in breadth first search algorithm, so as same as the previous one, we input vertex 1. As in depth first search algorithm, breadth first search algorithm also needs a Boolean array to keep track of visited and unvisited nodes. So that's why we also declare a Boolean array and call it visited. We know that breadth first search algorithm uses queue to track which node to visit next. Therefore, we declare queue data structure at the next line. At line number 5, we basically add our starting vertex into the queue as initializer of our while loop for the algorithm. At line number 7, we are executing our algorithm until our queue is empty using a while loop. At line number 9, we poll our starting node from the queue and have starting vertex equal to the vertex that we polled. Well, in this case, nothing will change for the start variable and it will still be equal to 1. Next, we can output the start vertex and set its visited state to true at line number 12. Next, we are declaring a linked list variable, this time called neighbor, and passing the connected vertices of start vertex in graph list as neighbor linked list. Here we are creating our for loop logic, which will iterate through the neighboring vertices of vertex 1. So at the next line, first index of neighbor linked list is vertex 0. This means dest variable will be equal to 0. At the next line, we check if vertex 0 is not visited. It is not visited. So then we add it to the queue and change the state of that vertex to visited, which means true. Next iteration will be executed since we still have one more vertex in our neighbor linked list. We basically do the same thing, get the vertex 4 and check if it is not visited. Add it to the queue and change its state to true in visit Boolean array. As we finished with this for loop, we get back to the while loop at line number 7. Next, start now will be equal to vertex that we are going to poll. We output the start and change its state to true. Well, it is already true, so we get to the next line. At the next line, we take again vertex 0 index of graph list and create neighbor linked list out of it. We get to the for loop logic and iterate through the connected nodes, add the ones into the queue that are not visited, and change their state from false to true. After iterating through the for loop, we get back to the while loop. Well, we still have some nodes that are in the queue, such as vertex 4 and vertex 2. Next polling vertex will be vertex 4. We follow same process here, print out the polled vertex, change its state and visit the connected neighbors. As you can see here, we already have visited vertices now in visit Boolean array, so for loop will iterate through and add the ones that are not visited to the queue and change its state to true. Well, at this point, the only node that is not visited here is vertex 3. So we keep iterating through the linked list and add vertex 3 to the queue. Back to while loop. Next vertex to poll is vertex 2. Well, the rest of iteration from here on will be for the sake of outputting variables that are existent in the queue. For this reason, we will be iterating through but not actually doing much. This is natural behavior of the algorithm design. So I will simulate through the code slowly and show you how we do not affect the outcome and complete our algorithm successfully when our queue is empty. At the next slide, I will present you the differences between breadth-first search and depth-first search algorithms. Then you can decide when to use which algorithm depending on the task you have. In this lecture, we learned how depth-first search and breadth-first search algorithms are implemented using practical tasks. If you had difficulties understanding this lecture, I highly recommend you to watch Algorithm Concept, Algorithm Complexity, Stack Abstract Data Type, Queue Abstract Data Type, and also Graph Data Structure before jumping into this one. So thank you for watching. I hope to see you in the next one.